So I'm going to continue with the previous chapter on file system interfaces and go into implementation of file systems. So this is where we left off last time. So there's sequential access versus direct access. So sequential access means you are reading one unit at a time, one by one word, one struct, whichever. And so the file head moves. Whereas direct access says you go to a particular point and you do read or write, and then you can position it to wherever location. And there are three ways you can position your file head. And so what that is it's called whence in your what's called seek. So there is an API called seek, and what it does is it allows you to move the file head even though you're not doing read or write, you're just moving the head. And there are three relative positions. So it could be relative to your current location, relative to beginning, or relative to the end of the file. Okay. And so in Python, you can open the file. You get a file handle back, and I refer to it as fh. And fh has a method called seek. And in C API, you have seek, and or higher level Cylinder IO, you have fseek. But the idea is the same. So if you do seek past 0 to it, what happens? Well, whence is default to 0. That means relative to beginning. So if you put it at 0, that moves the file head to the beginning of the file. And then when you do read or write next, it starts from the beginning. And how do you know where it is? Well, you can do tell or ftel, depending on which API you call it in C. In Python, then it's just the file handle .tell. That tells you the current position will be in a long integer. And then seek, you could do 0 whence equals to 2. What does that mean? So even though you pass 0, the meaning of 0 is defined by what's relative to. So whence defines it. So 2 means relative to the end. 1 means relative to the current position. Whence equal to 0 means relative to beginning. Okay, so you can arbitrarily position the file reading head. But if you try to go beyond the end of the file, no, it's not going to work. Okay, and so the meaning of whence is important in doing seeking. And so this is just really an illustration of what happens when you do a reset. That file pointer points to the beginning, which is index 0, so to speak. And then every time you read, it increments by 1. What is 1? Well, 1 is whatever unit it is. And write is the same thing. It advances the file head. Now there are other access methods, and it's called index method. And the way it works is it uses an index structure so that you can quickly locate the data. And so this is starting to be, somewhere between a file and like a database, but not exactly a database. But what it is you have an index, and that way the OS understands it and can go to a relative location, or whether it's the small master index, points to the disk blocks, or you have secondary index. So these are alternative ways for accessing your data on disk. So this would be an example. So there is your last name in the index file, and then each one points to an entry in the relative file. So that has a little bit of the database flavor to it. Now, but normally what you have is really a directory structure. And a directory can be thought of as a collection of these nodes containing information about all the files. So a directory you can think of as, you might call it just a container. It doesn't contain the files themselves, it contains references to the files. And files may reside different places, and in fact, different directories may reference the same set of files or different files. Okay, and now the thing to remember is that the directory structure and file structure both need to be saved on disk. so that once you power off reboot, that structure can be read back from the file system. So some people call it folders, but really folders is more of a user interface concept. And the concept of directories were invented way before these user interfaces. So it's, in OS terms, it's better to call them directories. And you can have subdirectories, but that wasn't always the case. But at least you have one level, and then you may have two levels, and in some cases just generally hierarchical. And the objective for having a directory is you only need to look at a smaller subset, so that when you do an open, given the directory, then you should be able to do a search within that directory pretty quickly. And this should grow or should scale well, even to a large number. In any case, the directory should provide some convenient naming for the user, and because the users are kind of required to come up with unique names all the time, or at least some program has to generate unique names, because the names are these ways of identifying the file in the context of a directory. Okay, so, and if you have two files of the same name, that can be problematic. And so a lot of user interfaces don't allow you to do that. It says, oh, that name's taken, you can't rename it, or by renaming it as the same name, it overwrites the older one, or the other one. And directories provide grouping, and the grouping may be that it has certain properties, and the files inside may inherit this, and so forth. But it doesn't have to be. Sometimes it's really just left up to the end user, what they want to use a directory for. So what can you do on the directory? Well, a lot of the same things that you would do to a file, but now in the context of a directory. So you can search for a file by name, by whichever. You can create a file in the directory, can delete a file from a directory, you can list a directory to see how many files or other subdirectories it may have. Rename the file, and so that is in the context of that directory, but then if that file also appears in some other directory, then this name probably wouldn't be affected. Traverse the file system, so that is you go into that subdirectory, subdirectories of that directory, or you can go up and down. And initially, you just have a single level directory, and like the first Mac, they did have folders, but these folders are really for visual use more than anything else. And so system-wide, you can't have files that are of different names, even though they're in different folders. So really? Yes, that was the case. And I was there. I had one of those first ones. So I actually used it. So of course that didn't last very long because people started having more files. This is not scalable, right? And besides, you rename it and it's like, what? There's nothing in this folder that has the same name. Why wouldn't you let me? Well, because it's in some other folder, right? So that's single level directory. It's easy to do, but has naming problem, grouping problem. So what if you go to two levels? And so assuming you're on a timeshare machine, multiple users, and so you can name the files all you want as long as you have unique names within yours, but other users can have same name and they wouldn't fight. But is that okay? Well, still, it's a little better, but not much better than a single level, right? But at least for different users, you don't have to search in their directories. And so pretty much universally, tree structured directories is what's done. And there you can have subdirectories within the directory, and then each one can have more subdirectories. It's a full recursive structure. And in this kind of structure, you can have what's called absolute path name versus relative path name. Absolute path name means you always start from the top. And so in Unix, it's always slash at the beginning. And that indicates you're going from the top, because slash is the name of the root. In other file systems, it may have a different convention. So like in DOS or Windows C:\\, that's an absolute path. Relative path means there's a concept of current directory. So like in Unix, you log into a shell, there you are in the directory. PWD print working directory that shows you the path for your current directory. So everything you specify can be relative to that. You don't have to go all the way from the top. And so that's more convenient, and you can change your working directory to some other one. And so whatever it is, all the file operations involve the context of the current directory, whether you specify an absolute path or you implicitly rely on the current path. So when you do an open of a file, say from any language, a lot of times it's assuming from whatever the current working directory is. When you do delete, you can think in terms of that Unix command rm, remove file. It only removes it from the directory. Now, if the file only appears in this directory, then yes, its space could be reclaimed. But if it appears in multiple different directories, then it continues to exist in the context of these other directories, but it doesn't disappear. It doesn't just get deleted right away. So it only removes from the current directory. Okay. Now you can make dir, so make directory that creates a new subdirectory. So these are Unix commands that really invoke the underlying API, and so that allows you to remove a subdirectory or make a subdirectory. rmdir to remove, mkdir to make. Okay. Now rmdir requires that directory must be empty, or else it gives you a warning. Doesn't actually do it, but if you do rm-rf, then forces and recursively removes the files before removing the directory. So somewhere the API requires you to have an empty directory before you're allowed to remove it. So a tree would be okay, but a tree makes things simple, because then you know when you traverse down, anything is strictly contained. You don't have other directories that may point. But I mentioned the possibility of a file appearing in multiple places. So if that's the case, then that means multiple directories may point to the same file. Okay, and so that is when it's no longer a tree, but it's becomes a graph. As long as it only points down, then it's acyclic. You don't have cycles. Okay. And so that way, these different, so the same file may appear, like for example here, in this directory count, and this other also appears as count. All right, so it doesn't matter if you go from this here or this from this spelled directory, they are the same. So if you modify it through this path, you can see the changes here. So I mean, this is like the pointer idea. You know this, and they have additional ways so that they can appear in different names in different directories. Now, if you have acyclic, it is Acyclic-Graph directories, and when you do a deletion, it is okay in the sense that you remove it from a directory, but you don't reclaim its space until all of the references to it have been deleted. So that's a lot like a garbage collection problem, right, for memory. Now, if you have you have a couple other ways too. You can have what's called back pointer. Right, back pointer means the file itself is actually pointing to all the directories that can contain it, not just a directory one-way pointer to the file. And so that way, but then you have the problem of, well, what if you try to do a link from many directories? How many back pointers do you keep? Right, so there's another solution, which is saying, okay, well, I don't just have direct pointers back, but I can daisy chain. Right, so it points to one, and then if additional link you follow until the last one, but then that one also has another link, so you have to keep tracing this in the daisy chain. But in practice, the more common way is to do what's called reference count. And again, that's very similar to how memory is managed also for garbage collection purpose. So in a more general graph directory, though, you don't have acyclic. Instead, what you have is you may have cycles. Okay, and so what happens? Well, if you have a cycle, then reference count is probably not going to work very well. Why? Because suppose you have this cycle, and it's isolated from everybody else now. So after this edge got deleted, okay, now you have this cycle. And guess what? The reference count is not going to be 0 because book points to AVI, AVI points to book. They each have one reference count. But nobody else can get to it, right? At least not from the root, traversing down. So that's garbage, right? And of course, this problem has been solved in garbage collection already. So you could do garbage collection type technique, and it's called mark and sweep. So you mark and then you sweep and do it in 2 passes. Anything reachable, right? You first copy, and then everything else left, well, that's unreachable, so you can claim that. So that solves the problem with reference count. So reference count may be simple, but it would cause a problem like this, so it requires a more expensive garbage collection. And what's another way? Well, another way would be to distinguish between what's called hard link and soft link. Soft link is also called symbolic link. So that means when you do a link in that directory, from a directory, the directory only indicates the path where the name is supposed to correspond to, but doesn't have another separate link for it. So that means if you remove the file, and that means you're removing these hard links, then any soft link that may still be around would not work because it would refer to a path that no longer exists. Okay, so that way it is maybe not as powerful, not as convenient, but at least it doesn't have this problem. Okay, so now you can also do cycle detection, and which you have done. Remember a couple months ago, right? I gave you that algorithm for depth first search. That's one way to do cycle detection, and then you can also traverse the directories, and then if there are links, you have a special mark for the links, and then skip them. That way, there's no no problem with the cycles. Okay, so next topic is protection versus reliability. So protection is really for the owner of the file to control what kind of operations are allowed and by whom. Okay, operations will include read, write, execute, because a program, executable program, is one is meant to be executed. So execute is one form of operation. And in addition to reading, writing, you have special form of append, right? That means to write to the end. And also delete and list a directory, for example. Reliability is a different problem in the sense that it's more of the kind of problem we talked about when we talked about RAID, right? So you may have bit error from the wear and tear of the device or from dropping a disk. So that's a different problem, but still it's a somewhat related one. So for protection, access control is really the term. That is, you want to be able to control how different users may access. Right? Access means apply some operation, read, write, execute, append, delete, and all those. Right? So the most general way to do this is to define the concept of user, which a timeshare machine would have. So it would know the different users. They each have their own accounts for authentication. Also the types of access, whether you're doing read, write, and how execute. These are the 3 basic ones. And for append, you might want to lump it into the writing. And also, there's much more general access control than file systems provide. And file systems provide you with the common types, but maybe in more general terms, you want to be able to control access based on the time or based on the location. But that starts to get a little bit more application specific. And also, you may, in addition, you may want additional forms of stronger access control. Like after you get the file, I mean, you can copy, you can do all you want, but then if you try to read data or make changes, it requires you for a password. And a lot of time that's protected by the application itself. And it could be for per file or per directory. And if it's per directory, then it always probably has to support it to some extent. So most file systems use some kind of access control list, but access control list could be could be arbitrarily complex in the general form. But what it does is it basically lists the users and what kind of operations are allowed per file. Okay, per file. That is so that means wow, there's quite a bit you have to track of for each file. So it needs to list the users, allowed modes of access. So we can assume just the three basic type: read, write, and execute. But just how many users are you supposed to track per file? Right? So that can be a lot. So especially if you have like thousands of users, then each file your access control list may be way larger than the file content itself. But in general, that's what happens, especially if you go to like cloud, right? So Google Drive, for example. In fact, every file would have its own access control list because you can explicitly share with an arbitrary number of users, but they don't care about space, so that's okay. But on your computer, you probably don't want to spend that much space, right? So what's Unix solution? Well, Unix uses a more condensed version, and that's called owner group public style of ACL, so access control list. So what it is. So first you have the concept of user, right? And the user here refers to the owner of the file. And if you create one, by default you're the owner. Or if you have super user privilege, you can actually designate the owner of the file. But it has just one owner at a time. And it identifies the user as well as the allowed permissions, again, read, write, execute. Now, in the context of directory, you can't really execute a directory. So execute means going into it, okay? And then for group, so remember the Unix version is user, group, and others, right? So group. So what is a group? Well, group is a separate concept. It defines a set of users or user IDs, and you can name them whatever you want. So like students, faculty, staff, right? These are just names. They don't really mean anything to the Unix file system or Unix OS as an OS. It just says it's a group of users. So user ID, a lot of times you have an integer associated with that, so that's what it keeps track of, and then separate lookup for the username. Now, a group can only be defined by a super user or system administrator. Okay, but you can then say, well, for this file, I'm going to allow the read, write, execute permission for particular group already defined by the super user. So for example, if you're a student user and you say, I want to share this file with other students in this class or other members of this class, right? Or maybe only with TA or TAs, and then yes, and so of course the same user can appear in multiple groups. There's no conflict at all. And then you define so everybody in the group would have the same access permission. So that would be the read, write, and execute rights, unless you are also in you're also the owner. Then of course the owner permission applies. But if you in a group, then all the members of the group uniformly have the same access rights. Now, others would be anybody else that's not an owner, not a group member, right? Then there's one set of rights defined for anybody else that's not there. And so if you do ls minus l in Unix, you see something like this, right? So it shows you these letters: R for read, W for write, and then X for execute. Or if it's a directory, that means go through, right? So the first three, I mean, not counting the leftmost one. The leftmost is an indication for if it's a directory or not. Okay, so but let's just look at everything else after the leftmost one. So you have three letters, and three letters. If it shows like R means that you have read access, W for write access. If it's just a dash, then that means you don't have execute in this case. Or the owner can read write X, but group has no read write X, and then others have no read write X, right? So in this case, doc read write execute for owner, read write execute for group, but for others only read and execute but not write. All right, so that's how you read this. And if you want to change mode, you can do chmod plus or minus the rights, and you can qualify it with which kind of user, whether it's the owner or it's the group or it's others, right? And then you can use a hex digit to specify the rewrite execute. So like chmod or group. So you don't get to define a group, but then you can change the group on the file. That way, say you may initially designate this for sharing with a class. Later you might designate sharing with others, right? So you can change the group and then the file or directory. You can set mode. You can do either the letter style or you can do the hex style. So chmod plus R, that means the owner and add the read permission. Minus R means remove the read permission. So owner, group, and public, or sometimes all others. And A means all of them. So if you do A plus R, that means add to owner the read permission, add to others the permission, add to group the read permission. Okay, so you can look at chmod. So if you do 761, 7 is 111, so rewrite execute. Set all three. 6 is what? 110, right? So read, write, but not execute. And what's 1? So 001. So no read, no write, but execute, right? Okay, so that is the file system interface. Next topic is the next chapter, which is chapter 14, file system implementation. So this shows you details on how a file system is implemented, whereas the previous chapter is more on what kind of operations does a file system provide and support, right? So now the file system implementation, well, there's quite a bit, although compared to the previous edition of the book, they made a lot of rearrangements. So for example, network file system, that got moved, so that shouldn't be there. But these some other ones are still in there. Okay, so file system structure, well, again, a quick recap. It's structure residing on secondary storage. And second, as any device, you have the physical mapping, but the file system provides a logical mapping, and it provides an efficient implementation and convenient API. And one OS may support multiple file systems. So for example, you may have a Windows machine that uses NTFS, but if you stick a USB stick, it's probably FAT32. And on Mac, it has it's a HFS or HFS Plus and others. But if you stick a FAT32 USB stick, it'll understand it. Okay, so an OS can support several, and Linux probably uses ext3, ext4. But you use USB stick, it's all still FAT32. But then if you format it as like a Mac file system, put it on Unix, it probably won't understand it. And now a disk is a place where you can save data and also support this write operation, whether sequentially or random access. And at least magnetic disks assume you do what's called writing in place, very much like memory. That is, if you want to write over something physically, you're writing over that same sector or same physical storage. But for Flash, that's not always the case, and file system takes care of that kind of mapping. Whichever it is, there's the unit of blocks or a basic transfer unit, and that may be one sector or multiple sectors. And two design problems in file system would be the interface to user program and interface to physical storage, right? User interface to user program, we've seen open, read, write, and then this may encompass append as part of the open, and then you do write to it. And this interface to user program mostly independent of the file system. And if you write it in C, standard I/O, that is one way to use an API that is more or less always independent. Now, if you interface to physical storage, then that actually may need to get to be more device. Well, it's still mostly independent of the actual disk because there's standards for the commands. But then each one may have its own specific operations. So file system is usually layered. So user sees the API layer and up for the higher level, like the read file handle, the buffer to read into, the size to request reading for. And then there's the logical file system, which has the manages the metadata, not just the raw storage, and it may have to manage some caching. And also perform allocation, freeing, and also the replacement policy, right? And so below the logical file system, you have file organization modules, and that would perform the mapping between logical and physical concepts. And so that is, you translate, or this layer translates the logical to physical block number, and it just free space this allocation. So the commands that it sees would be to do like a read for which disk, which cylinder, which track, which sector, and so forth, right? So that's why you see these much lower commands. These are actually the physical concepts. And that's implementing the very, very basic file system. And then the I/O control part, this is really in the physical layer. So read drive 1, cylinder 72 track, and then all into memory location. And then these are organized in terms of the basic transfer units are called blocks. And these blocks may be numbered, and then there are commands for working at this kind of block level. Right? So you can see the concepts go progressively down from the higher level down to logical, down to physical. Logical file system has to maintain a lot of metadata, and including the file number. When you access, you either give a file number or file handle. So standard I/O, you have capital file star, right? That's a file handle. And if you just do, so that you can do fopen, fread, fwrite, and anything starting with F. So that's with the file handle. But if you're using the lower level API in Unix, that's just the read, write, and there's no F in front. So that takes a file number instead of file handle. But in either case, the OS actually has to maintain the information, and that's in file control blocks. And so FCB, right? And in Unix, they use what's called inodes, and I'll talk about that. And there's directory management in addition to the file, as well as the protection we just mentioned. Layering, it can be useful for the user, and also you really shield the user or even application programmer from a lot of the complexity of having to deal with the individual disks and having to manage the physical media. But you pay a price for it. Is it worth it? Yes, most of the time it's worth it. But if you're so performance critical, then yeah, you may want to bypass that. So like swapping, a lot of times bypasses the file system and doesn't even track a lot of this metadata. Now, I mentioned an OS can support multiple file systems. So like if you have CD-ROM, that's an ISO 9660 standard. Unix has a Unix file system and the fast file system, FFS. Windows started with FAT16, but then it ran into a limitation beyond so many megabytes. Hard disk get bigger, and then FAT32 replaces FAT16, but then it's starting to run into its limitation. So pretty soon, FAT32 might not be enough. But way before then, they came up with the NTFS, and that's supposed to scale much better. Right. So there was an OS that Microsoft developed in conjunction with digital equipment. That was NT for network, T technology. So that was before digital equipment, which made VAX VMS and a lot of very popular machines. They were trying to get into the more desktop business. So Microsoft promised to port this to their Alpha processor, which was the fastest workstation processor at the time. And of course, Microsoft worked with a few other companies before, like worked with IBM, got OS2, made a lot of promises, but then intentionally broke a few things. So then even though OS was way better OS, people were scared to switch over. But Microsoft learned a lot of things from OS2. And NT, again, very robust system with a lot of the experience from digital equipment, including the file system. And then, and that was done in the late 90s. And Windows XP also was the first one to bring it to the more mainstream Windows. NT was used, but then there were a few things that weren't done quite the same way. So now for more future-looking, yeah, NTFS is what they recommend. Although for these USB sticks, you probably don't put NTFS on there. But before then, of course, there's floppy drive, right? Floppy had its own file system, CD, DVD, Blu-ray. Now, Linux uses these ext2, 3, now up to ext4, and there's other distributed file systems. And new ones still being invented, so there's ZFS, Google file system, Oracle has their own, and network file system, NFS, that's one of the pretty important ones at the time of these stations. So Sun Microsystem did NFS, but that was more over the network, and that is not covered in this chapter. It used to be, but got moved out. Anyway, so the point here is there are lots of file systems. Of course, there's Apple ones, HFS, HFS Plus, all the other ones. The book actually has a sidebar just on HFS. Okay, implementation. So remember, there's structure you have to save on disk, right? So what are these? So there's boot control block, volume control block, sometimes called partition control block, directory structure, file control block. So a boot control block is really one per volume or one per partition. So what's the difference between volume and partition? Well, for all practical purposes, they're pretty much the same, except if you really want to make a distinction, partition is just the raw part. You divide up the disk into partitions, and then if you put a file system on a partition, it's called a volume. So that's really a quick way to distinguish them. But for most part, they're the same. So so a boot control block contains information needed by the system to boot some OS from that volume. And so that's needed only if you try to boot from there. But if you just store data, you don't need that, right? If you never need to boot up from there. Now, volume control block or partition control block, that is, as you can imagine, one per volume or one per partition. So that's more of the information that defines that volume. Super block, master file table, right? All the details, how many blocks, how many free blocks, block size, and also how do you keep track of the free ones? You have block pointers or array or which. Now you have a directory structure. So now it's one directory structure per file system, and a directory structure is really one that tracks all the different directories. Okay, and what do you need in a directory? Well, the name, the inode number, the master file table. And you also have what's called file control block, and that is one per file. Okay, so in Unix, these are called inodes, and so you have one per file, even though it may appear multiple times in different directories. So every appearance, that's actually is information stored in the directory, but it references the file control block. So that's how you can identify if they're the same or different files. Permission, size, date, and so forth. Okay, and NTFS uses a relational database structure for storing the master file table. So on this structure here, right, another illustration. So partition or volume would have to have this information. So from the beginning, you have the boot control block. That's optional. If you want to have an OS, right, you put that boot control block there. There's partition control block, list of directory control blocks, and also list of file control blocks. Right. So the directory structure is one, and then it has the list of these directory control blocks, and sometimes they call D entry. I think at least in the previous editions, this edition I still have to look. But FCB, file control block, that you know, so it has the permissions, the date, owner, group, access control list, size, blocks, or pointer. So where the file data actually resides. And in addition to these structures in memory, the OS has to read them. On disk, OS has to read them into memory, right? Because to do anything, it has to be memory resident. So that means the OS actually has to construct additional data structures. Some are just, you might say, cached copies of what's on disk. Others are specific to the way the OS is operating, the state of the OS. So for example, there's a mount table. That is an in-memory structure. That's not on disk. A mount table keeps track of which volumes or which file systems have been mounted and where. So for example, if you log into a Unix machine, you look at the directory structure. Well, it looks like one tree to you, right? Root and then the various things. But guess what? Some of these, if you can capture their state as you're booting up, initially it doesn't have much. It just has the root, a few things. And then it may mount additional file systems in. Some may be virtual, some may be physical, some may be over network. And so what it does is it already has these empty ones, but then it mounts a drive in the place of these empty directories, so that it looks like a one coherent tree. But in reality, these are mounted over time as the OS runs. And if you insert a drive, yes, it gets mounted, right? And then initially it may look like an empty directory, but then it gets connected there. So it's part of that integrated whole file system. And if you reject, yeah, it's gone, right? So a mount table keeps track of what's currently connected and as part of your whole tree, or if you reject, you remove it, right? So stores the file system mount points. That is, which path do you place that, and then also the types. So it knows if it's a CD-ROM, it knows if it's a USB stick, it knows it's external hard drive, whichever, right? So these in-memory directory structures would be what. So I mean, the OS has to read from the disk to see, what directory you need, and so it's a copy of it. It operates in memory, but then it has to keep it in sync with the disk, right? Also, the open state of these files. So a system-wide open files table. That is one where, as you call the open system call to open the different files, then each time it's open, the state information is kept in this system-wide. So one OS, one system-wide open file table. Okay, so different processes may request it, but OS keep track of all of them in one place. So it contains a copy of each open file's file control block. Now there is also per process open file table. So that contains the file handle to the corresponding entry in system-wide table. So that means like different processes may open the same file, but then they each have a different file pointer. So if I do reading from one process, only this process controls where file head is. You can keep reading and moves, and if I don't read, it stays there. Another process has a separate file handle to that same file. So when it reads and writes, it doesn't affect this other process's file handle, right? They are kept track of separate. That's why you need one per process. In addition, in-memory structure includes of buffers that hold data blocks from secondary storage. So I'll talk about that. So there's buffer caching, page caching, and so forth. Okay, so open, if you call open on the file name, what happens? So from user space, the kernel, well, it has to bring in the directory structure if it's not already. If not, has to grab it or load it in and examine it. And then it looks in there. Is this file name in this directory? If so, yes, I can try to open it. And then assuming you have the permission, otherwise you can reject and say, oh, sorry, you don't have the permission. But assuming it does, then that contains information to secondary storage. And then you may need to also, every time you access something, you may actually have to update metadata. And this could be in the directory structure. So even though they draw the arrow this way, it actually is just indicating that it says update needed and they need to be kept in sync. Okay, and OS has to do that. So there's a lot of bookkeeping needed just to access little things like this. To do read, so now you don't use the file name anymore because you have the index. In the case of fread, then you have to you pass the file handle, whatever it is. So they give you the eventually the same thing, from which the system takes over, and then that's the system-wide open file table, right? And from there, it points to where your data is on secondary storage, and then the update file control block. Every time it is accessed, right, you may have to update the last access time, or if it's writing, last write time, and so forth, right? And then again, this arrow is a little misleading. I think you can read the text for more detailed explanation, but it's just saying the in-memory structure and the on-disk structure need to be kept synchronized, right? And if you don't, you can have a problem, and we'll talk about that later in this chapter.